The goal of this video is to prove a very famous result, which is that if a function f is differentiable at some point p in its domain, then it's continuous at p. So this is a well-known property of differentiable functions, and I will show you how to do the proof. I'm actually going to do the proof twice. The fast way, just to get this statement. So what is like the fastest way to take this knowledge and extract continuity from that? And then as a bonus, because otherwise the video would be really short, I will do a longer proof of the same statement, but one which gives us this kind of funny phrase here that if f is differentiable at p, it's not just continuous at p, it's what you could call locally Lipschitz at p. In my opinion, that's not a global like piece of terminology. So locally Lipschitz at p is sort of a funny thing to say because there's another property called locally Lipschitz. So when I write down the final property, I'll tell you what I mean by this language. What we are going to do with our proof here that f is continuous is take this as fact because we are going to assume that f is differentiable at p, which means we know this to be true. So knowing that this limit is 0, what can we back out of that? So that's what we will do twice, one very short, so what's like the fastest way to get continuity, and one which is longer but gives us a little bit more information about the type of continuous that f is. Okay, here is the quick proof that f is continuous. A couple different ways to organize this information, but they all rely on the same principle, which is that if that quotient is going to 0 for differentiability, then the numerator is going to 0. So that's really the key argument. I want to establish that as x goes to p, the limit of f of x exists and equals f of p. So what I'm going to do is bring in a couple of copies of 0. So let me subtract f of p, and then I will add it back. And likewise, I will subtract df at p times x minus p, and I will add that back. Okay, so that overall this is just limit of f of x equals limit of f of x. But the reason I did this is that this whole expression here is what we have inside the numerator in our limit for differentiability. Since that norm is going to 0, what we are computing the norm of must be going to the origin in Rm. So we know this goes to the origin in Rm. This is just f of p. And now this is a linear transformation acting on something going to the origin in the domain. So as x goes to p, x minus p goes to 0. A linear transformation is a continuous function, and it sends origins to origins. So as this approaches the origin, this linear transformation is going to send us towards the origin in Rm. Okay, so linear transformations are continuous, and they map origins to origins. So that overall, we can now compute this limit. It's, let me just write it out, the origin in Rm plus f of p plus the origin in Rm again. So it's f of p. And that's it. And like I said, you can look at a couple other proofs of this statement, which might look a little bit different than what I did here, where I kind of brought in a bunch of terms, but they're all likely, if it's short like this, depending on the same idea, which is that if f is differentiable, then it's really well approximated by this linear transformation, and you can set up this limit as x approaches p and basically drive the whole function towards f of p just by knowing that that numerator expression in our definition of differentiability goes to 0. Okay, I think I've said more than like you even need to write down to prove this statement. But as I promised, I'm now going to make the argument more complicated to arrive at a statement that f is not just continuous, but it's like a little bit stronger than continuous. So there's a little bit more that we can say about it. I will come back and take you through that argument and explain even what this property is. All right, to wrap up our discussion with this idea of being locally Lipschitz at p, let me remind you of two facts that we've already seen. Since df at p is a linear transformation, so linear transformation, there exists a number m greater than 0 so that the action of this linear transformation doesn't scale outputs by more than m times the length of the original input. Let me write that out mathematically, such that df at p times, let's say, vector u in Rn, this norm, which is a norm where an Rm is less than or equal to capital M, this number here, times the original length of u. That was something that we discussed when we talked about linear transformations. Okay, so that's fact number 1. Fact number 2 is just reminding you of our epsilon delta description of differentiability. So when we introduced differentiability, I said, here's my form, the form that I like to work with, but there are other ways to express the exact same notion. There was the epsilon delta characterization. Since we know that f is differentiable at p, I know that for any choice of epsilon, I can then go find a delta so that, et cetera, et cetera. So let me make a choice of epsilon. Okay, so since f is differentiable at p, we know this. For a specific choice of epsilon that I'm going to make, there exists a delta greater than 0 so that, well, for one thing, we're working in an open domain. Let me insist that delta is being chosen so that we stay in the open domain. So how about the ball of radius delta around P stays in A, and more interestingly, like what I'm really trying to get at with this epsilon delta description, when I look at the numerator expression, f of x minus f of p minus df at p times x minus p, this norm is less than or equal to epsilon times the distance from x to p whenever that distance is less than delta. So let me say for all x in this delta neighborhood around p. Okay, so these are two facts that we know because we're working with a linear transformation, so this is automatically satisfied, and we know already that our function is differentiable at p. Therefore, here's what we're trying to show. The distance from f of x to f of p is equal to, let's bring in fancy 0 that looks like this, like subtracted and added back. So I'm going to subtract df at p times x minus p and add it back. Break this up with the triangle inequality. So less than or equal to this norm. And then plus this norm. Now we use the two facts that we have. Here, maybe I should add this if I'm writing this up appropriately. For all x in this delta ball around p. Oops, sorry, I meant for all x. This expression is less than or equal to just the distance from x to p, and then plus m times, what we're acting on with our linear transformation, and that is exactly x minus p. But now I have two expressions I can actually add together. This is m plus 1 times x minus p, that distance. I've been omitting what norm we're working in. Let me just add that here if it's helpful. This is in Rm, this is in Rm, Rm, Rm. But when we make this step, we're actually now looking at norms in Rn and ending up with a norm in Rn. Okay, if you start here and end here, it looks like a statement about Lipschitz continuity. So it looks like saying like the distance between outputs is less than or equal to some fixed number times the distance between inputs. But it's not exactly that for two reasons. One is that when you have Lipschitz continuity, these two inputs don't necessarily have to be close together. And here we're saying that they do. So saying that this is only true when the inputs are suitably close together is like locally Lipschitz, but it's not exactly that either because P is not arbitrary. So here P is fixed and I'm letting X be anything within a suitable distance of P. So that's why I'm calling this being locally Lipschitz at P. It's like a Lipschitz statement, but P is like one choice of the inputs that we need for the Lipschitz type comparison that we're making here. And then X has to be close to P. Okay, so it's a very like kind of niche form of continuity, if you will. The reason why I'm bringing this up is that sometimes we will actually need this bound for a differentiable function. We'll say, oh, we're comparing two outputs for a differentiable function. Let's remember that differentiable functions have this kind of local Lipschitz at P property. In particular, we will actually use this when we prove the chain rule down the road. So I wanted to mention it here because it is a little bit random, but it's also saying that not only is F continuous, but we have like a slightly stronger statement than just plain old continuity. I think I will leave this here and, we have a lot more to talk about in future videos about differentiability.